Hi, welcome to the Earth Science Classroom. Welcome back. We're looking at the Earth as a System playlist and geomorphology. We're looking at today at a term called equilibrium. It is a term that you may encounter in different kinds of sciences, especially chemistry, even biology to some extent, earth sciences, geosciences, engineering, and physics. So it's a very fluid term. And we look at this term equilibrium in relation to geosciences and earth sciences and physical geography and what it means and how it relates to Earth as a system. And what we're going to do is this. We're going to basically explain what it is, right? What is this term, right? What is the term? How does it relate to thermodynamics, which we discussed in a different video on Earth as a system. We're going to look at the different types of equilibriums, for EQ for short. Look at some examples and how we can relate this to geoscience and the natural world and what's going on in real terms and real time. And look at how we can apply this throughout our course and link it up to other topics. For example, hydrology, perfect example. Atmospheric science and meteorology, even astronomy, and other courses, other topics as well as that. All right, guys, so join me now for the video. All right, so what is equilibrium? Now, equilibrium has different definitions based on the sciences that you are studying. In physics, there's a certain definition. In even game console and gaming, it has a certain definition. But in geosciences, you're looking at the term steady state, which implies it's kind of a term that is used as well as equilibrium. Now, at the basic level, you can tell your students that they are the same. However, at the advanced level, this is inaccurate based on the Earth, the planetary spheres working together, is a complex, dynamic system. That is constantly changing over time. Now, the issue is, the great thing about geosciences is a lot of the topics and material we work with is in your face. You can see it change. You can hold it, feel it, experience the information that's put in front of you, like rocks and minerals and volcanoes, earthquakes and tornadoes and astronomy. You can see the stars and see the moon and the sun. However, a lot of things are a lot of abstract terms, a lot of topics that are hard to explain or hard to imagine. For example, geological time. You're looking at a very large time scale. Humans don't always appreciate the sheer time it takes to things to change. For example, the Himalayan mountains are currently the highest or tallest mountains in the world, but in the past they weren't. They weren't even around prior to 15 million years ago, which is not a long time in terms of the Earth. So the time scale and how things change, how our landforms change, can be a little bit abstract for students to comprehend. So the idea that the Earth is in some sort of equilibrium, yes, that is time sensitive. Looking at 1 year, or let's say a decade, or a century, yes, there could be no change. And there could be seen to be a point of equilibrium between the spheres where there is limited change, or there's a small change, okay, over time. Let's say a flash flood, for example, flash flood in Arizona or Colorado, that it will eventually come back to being a dry, arid environment after the rainstorm and flash flood has passed. So there are small fluctuations, but over time there is a consistent balance in nature that would create this equilibrium or steady state. Now, if looking at the physics part of this, I'm looking at a thermodynamic equilibrium. Again, in an idealized, closed system whereby the surroundings are not interfered with, not exchanged with, not connected with, and you have energy and matter are contained within that system. So, according to the second law of thermodynamics, which is based around entropy and disorder, over time, okay, the system will become in equilibrium once it's given enough time. So let's say here's my graph. Here's my starting point up here, and it's going to go down like this. And it's going to, for best example, it would be, let's say, decay. So the system will become more and more decayed, more and more broken down, more disorder from the initial point of inception or start, and it's going to decay and decay and decay to a point where it's become disordered, and has come to a point of, let's say, equilibrium right here towards the end. Now, this also relates to the third law, which follows along, whereby at absolute zero, in terms of the temperature, you would have no more change within the system. Because when you're talking about thermodynamics, you're really talking about thermal energy. Thermal energy, which can be transferred or moved to either kinetic energy or potential energy. Now, this again goes to the first law, which means that you cannot create or destroy energy. It just gets transferred into a different kind of energy, so thermal to kinetic. So now going to the types of equilibrium. So in nature, now it basically started with open and closed systems. And the history of geomorphology, the history of landscapes, and all these pioneering scientists, both from America and from Europe, basically studying the landforms and studying the changes and the fluvial systems and the origins and the mountain building and how erosion and weathering took place and changed the landform from destructive to constructive, and how it all played into the systems, how the planet is a big system, how the different spheres, different components add up to work in a sphere, and whether it is open, where there is a exchange of energy and matter, it's free, everything is fluid and moving over time and space, and closed being obviously that separated environment where energy and matter are contained, which is again based on thermodynamics, thermo D right there. So it all starts with that. Now, basic types we've already mentioned before. I'm going to draw a graph because it's better to show it with a graph. Okay. So here's my graph. Okay. So I'm going to put energy or number of energy there. So we have low energy and we have high energy. Okay. And down here on our x-axis, we have time. Okay. So if we're looking at equilibrium, we're going to look at, obviously I've mentioned the first one, let's do steady state, which is the whole premise of what's called the general systems theory, which was proposed in 1899 by Davis but then was later developed by some scientists like Gilbert in 1870. Well, 1876 was the first one to 1880. So those two are the kind of the main driving forces behind this new idea that within an open system you have this natural balance that is created by different spheres, and the environment comes to a point where there's little change, and the changes are balanced out over time. So a steady state would be like this. You have this small fluctuations, but it's pretty linear. There's small fluctuations, small changes, fluctuations, alterations to the equilibrium. But generally you have this somewhat linear, somewhat consistent. There's changes over time, but overall you have this very consistent kind of environment or system of play that's working on that landform. Okay. Okay, number two I'm going to look at is just completely linear. There's no changes, there's no fluctuations. It's complete. This landform does not change. There is no changes. There is nothing that affects this landform. Is exactly the same throughout the whole time, and we call this static. Everything is balanced, everything is kept in check, and that causes the environment to experience no changes over time. Again, this is extremely rare to find because our planet, with the mixing of systems, the complexity of how things work, the functionality, the disturbances, the nature of chaos, and very erratic time and different time scales, is so hard to find this. It's just a type, but we rarely see it. All right, next one is called stable. Now, stable is like this. Now, obviously, you can tell that it's very similar to steady state. There is a large fluctuation, large change compared to static, but stable is where you'd have a distinct change to the system, change to the landform, but over time, as you can see over time, it slowly comes back to being more consistent, more uniform, more stable, and comes back to its equilibrium. So this would also be a great example of a negative feedback loop or negative feedback, where you have an initial disturbance or change to the landform, let's say a flash flood, let's say a tornado, for example, or a cold front coming through on a mid-latitude cyclone, or let's say a dust storm, it's like that, which is very very discrete in terms of time, when it starts, when it finishes, and you'd have this stable equilibrium. Our next one is unstable. So you've got this initial equilibrium, and then we go up, and then we go this. So we're looking at right here, in this little area here, we've got this stable, maybe even steady state equilibrium. What makes this unstable is the fact that there's enough energy, enough change within the system that it is caused there to go beyond the threshold or limit or parameters of that landform, of that system, and it's changed to a new. So it's gone. So I just continue this line where if it was like a stable or steady state, it will come back down. It doesn't. If it was steady state, it will just keep on rotating, or fluctuating. But unstable means that it's now gone to a different landform. Let's say grade one is a beach, where you have a bunch of of moving sand dunes or moving sandbars under the water, or you have beach erosion, where the beach is one condition or one certain um, structure one day, and there's a big storm, and it completely changes the whole coastline and erodes it, and you've got a new coastline the next week after a large hurricane, for example, or cyclone. So unstable is very common, where it's gone past the environment's threshold and created a new landform. So it'll be a new landform. Could be similar, like the beach, it's still a beach, but different features, and it's different from the time before. So unstable is very common as well. So these are the four kind of like, I would say, not basic, but the introductory terms and types for equilibriums. The ones you start with and give examples for, and then you can move on to the more, let's say, complex ones. So the first one is going to be this one here. This one is called dynamic. Now, the modern interpretation of steady state, which was first introduced back in the late 1800s and then developed over the course of the 20th century, as we learned more about geomorphology, learned more about the processes, the time, stratigraphy, and how the layers of rock and ice give a better idea of what happened in the past and how things worked, and the time it takes for these cycles to unfold. The erosional cycles, fluvial systems, even tectonics, to build up the landforms and then to slowly destroy the landforms through weather and erosion. So dynamic is more of that modern term to explain in more detail and what actually happens in landforms, our steady state. Okay, our equilibrium. So we appreciate that over time there's going to be changes to the landform, and within those long-term changes there'll be short-term fluctuations and very dynamic changes within the system. Some things can change quickly, some things can change slowly. Rivers can meander, rivers can change course, erode quicker, faster. Depends, again, it's more complex because it depends on more factors, depends on more parameters. How a river actually erodes the environment is based on the bed load, suspended load, the velocity of the water, the amount of water, is it a perennial river? Is it going to be over certain kinds of bedrock and terrain and gradient and slope and the gravity effect? So there's a lot that goes into it. That's why dynamic is more appropriate to explain what happens. All right, the next one is going to be this. It's going to be called metastable. Now, meta means different levels, different parts, multiple times. It's more of a plural example. So stable, again, we're looking at that balance in nature for landforms being very consistent in their appearance and processes. Metastable means that there is some sort of very abrupt change that can happen. For example, let's say a meteorite and collision, and you've got, let's say, a small one that's not a global killer, like the dinosaurs with a KT extinction, but there's a small one, let's say it's the one that went over Russia in 2013, for example, a small meteorite where there'd be initial crater, initial destruction and disturbance to the environment, but it will get back to the same sort of thing after the fact. After weather and erosion, the crater would then become part of the landform, and you'd have a new stable environment after that initial change. but you still have these very small, minute disturbances either side of the abrupt change, and of course, it would go through the different thresholds of that landform. The next complex type of equilibrium is episodic, so it goes through certain episodes, certain states, where again you have the threshold or two thresholds you see there, the dotted lines, but this equilibrium, this landform is obviously fluctuating, but it's obviously going to increase and change abruptly, well not abruptly, but very change over time, but then have this overshoot up here, come down and then reorganize itself into a state of equilibrium. So there's various changes that go on in this one where it can go through different cycles that can affect the landforms. The next one's pretty cool. Does this and does this, comes back and does this. This is called dynamic metastable. Dynamic metastable. So meta can also mean that it's after or beyond. So it's stable after the fact that there's a change in the landform. There's been a push past the different thresholds of that landform, push out of its equilibrium. But you see these small disturbances, these small changes, and then there's two abrupt changes. One up and continues for a short time, right? Short time, and then there's a rapid kind of like resorting out, going back to the original, kind of like dynamic equilibrium as it was prior in the past. So this one could be an ice age. Great example would be an ice age. The northern hemisphere goes through an ice age, like we have done for the last 2.6 million years, a cycle of ice ages, interglacial, glacial periods, and that will be a great example of dynamic metastable equilibrium. So the last one I want to show you is this beautiful design right here. This one is chaotic. Now, it really has no real equilibrium, so just call it non-equilibrium. So it doesn't really, the landform does never really become stable or balanced within the different processes, the changes. There's never a point where there's no changes. It's constantly changing all the time. This could be an example of, let's say, primordial Earth. In the first few 100 million years of the Earth's lifespan, it was changing so fast. Nothing was balanced about it, with the impacts of the meteors and the molten surface and the arrangement of the elements and how it cooled down. But this also reminds me of a great quote from Jurassic Park, the movie, with the mathematician character played by Jeff Goldblum, was saying that he was a chaos theory advocate, saying that with Jurassic Park and the animals, the dinosaurs, that life will find a way, that chaos will ensue within nature, and there'll be a pathway made from chaos. You can also argue that evolution and our even existence has come from a chaotic past. We're just a mixture of great random chances of evolution and fate, you could say. A little bit deep, but I apologize. Just love that movie. All right, so that is all the different types of equilibrium. There's the basic ones, there's the ones more complex, and the last one here is that's chaotic, which obviously is hard to find an equilibrium over a course of time. So we use these to understand the Earth and the process and how things are formed and get destroyed and then remade over time, because we know that the Earth is inherently both complex, interconnected, and also unstable, and is a dynamic part or dynamic essence to this planet. And to understand it is to understand geoscience and how things function. All right, thanks a lot, guys.